Start recording. Good morning, physical science class. We started a little bit late, about 4 minutes late, because I was running into some issues with the internet. And I hope that it's going to stay on at least toward the end of the class. Anyway, if it does, if you are live, please don't leave. I know some of you left earlier. So, I will hope to try to recover from it. If it does not, then at the end, basically, I will just record the information that we need and basically share it with you guys and post it on Canvas on the proper place, okay? So this is the plan, and it's true all the time, so it's not just for today. Sometimes there's problems with the internet in here. Anyway, so we are in week 9 of physical science. We have an exam that is not too long from now, not next week, the week after. So again, similar to the previous exam, I'm going to post the review. Hopefully you guys will do the review, and then when we do the exam, you're going to do the exam. Again, the reviews are graded and graded for participation. So work very hard to make sure to allot the time for them and do them. And then the advantage of doing that also, in addition to the fact you get full credit for doing them, regardless of what you score in them, is to prepare you for the actual exam. So that's the idea behind it. This week, if you guys have had a chance to go through the Canvas and see what's posted, you will see that there is a homework, again, from the previous week. The homework this time around is a little bit more involved, which means that you have to, there is more work in it. I'm going to go thoroughly through it. I'm going to discuss the homework. And if you, in case you forget while you're doing the homework later on, it's a good idea to come back to this recording. That way, you know what's there. It's still, you may still have lingering questions, even though you watched it, you attended it live, and you did. But for some reason, something did not add up or something does not come out the way it's supposed to be, then please reach out to me to make sure you have full understanding of the homework. Again, the homework is supposed to be an open-ended, basically you don't have a time limit on it. So you can spend as much time to take it. You can review resources. And even if we were on campus, so this is not because it's an online thing that I do that, even if we were live, so it's still, the homework is not supposed to be, if you wish, an exam. In a sense, you go review the materials, you check the book, you check the resources, and then you answer the homework. So that's basically how homework works, okay? So again, we have an assignment this week. I'm going to go thoroughly through it. It's due Friday. Is it Friday? The 20? No, it's actually not Friday. The 22nd of the month, which is actually, yes, it's a Friday. Okay, it's Friday, October 22nd. That's when the homework is due. So we really have to make sure that we're covering it. We are still dealing with electricity, with the other side of electricity. Think of electricity and magnetism as two sides of the same coin, where electricity is shown one side and magnetism in the other. That's all. So we're going to talk about this point in here. So let me share where we are. And let me put the, okay. So let me go back into the objectives for the week. Okay. For some reason, it takes a long time to upload these images, which hopefully you guys have had a chance to go through them. But again, because the internet is lagging, so we'll have to work around this thing. Okay. Again, I just mentioned the homework, and I'm going to come back to the homework to discuss it. Chapter 9 deals with magnetism. Magnetism is as old as men can remember. I mean, ever since materials have been discovered to attract one another and attract themselves to metals, magnetism was discovered. And magnetic materials come in different shapes and forms. You have all kinds of forms. They are mainly basically nickel, cobalt, and iron. Those are the materials that retain their magnetic properties. Some other materials, they don't, I mean, you don't have permanent magnets out of them. You can have as long as you apply an external field on them, they can be magnetized. And then if you were to remove the magnetic field, they lose their magnetism. So those are kind of magnetic materials, at least most of the materials are. And they're called paramagnetic materials. And then in addition to that, you have some materials that behave backward. In a sense, you apply magnetic field in direction, and the polarity you come up with is backward. In a sense, they are opposite to that. And this, they're called the anti-ferromagnetic materials. And then you have all kinds of materials in between, basically, okay? So different properties, okay? So here is a typical magnet. So let me change the camera to show the idea behind it. Go back basically without camera. So here is a magnet. Magnets, as you can clearly see, is characterized by two poles, a north pole and a south pole, okay? So the north pole, if I bring a compass, I thought I had one here. I have one somewhere, but I don't have it right now handy with me. Put this back. No. There's another bag that I put today. No, it's not in this bag. Anyway, the idea is, if you're not too familiar with a compass, I mean, it's just a needle basically that is suspended in a solution, and that needle basically will point to where the North Pole is. So think of a needle, you have it in here, and it's pointing this way. If I put it next to the South Pole, it's going to post in the opposite direction. I call this one north, and I call this one south, just because how the needle behaves in front of the towards Earth. Basically, it points to the North Pole and the South Pole. Okay, so in this case, that's how the needle works, really. And that's how we came up with the names, North Pole and South Pole, based on the geographical names. I mean, they are two different things. That's basically what they are. And we needed to distinguish between them. Since the word positive and negative at that time was already allocated to other things, okay? And at that time, I mean, positive and negative also, especially for the charge, has this kind of a, an inferred meaning, as if the protons, because they are positively charged, they have more of something, whereas the negative electrons, they seem to have less of that same thing. But it is not that. It is they have two different things. That's it. They're opposite. That's all. So whatever this one has, the other one has the same thing, but are opposite to it when it comes to charges. The same thing is true for magnetic poles. Whatever this thing has, the other one has, but it's in opposite direction. That's all. That's really what that means. Since we already use positive and negative, so we call them north and south. We could have called them left and right. We could have called them up and down. We could have called them, at least as you have two opposites, okay? So whatever you want to call them, that's basically to distinguish between them. They are equal the same way, okay? In every single respect, except that they're distinguished from one another from this kind of opposition that they exhibit, okay? Now, is it possible for me to take this magnet and cut it in half and isolate the blue side by itself and the south side, the red side by itself? Basically, I will end up with a positive red and a negative blue. Is it possible to do that? Well, experience has shown that this is not possible. If I cut it in two, the blue will acquire a new color, which is red. It's not really color, but the color is artificial, by the way. It's made just for our convenience. So in other words, when you make the cut, two poles will appear all of a sudden. Whereas you're supposed to have south on this side, you will have a new north in here in the middle. Whereas you're supposed to have a north in here, a new south will appear in there. So you say, okay, I didn't end up with the North Pole by itself and the South Pole by itself. Can I do this? Can I take this a new magnet now that formed, because the new magnet now has a north and a south, Can I cut that into half? Basically, you will end up with a quarter with what you started with, and isolate in that case the North Pole and the South Pole by itself. Well, experience has shown that this is not possible. Okay? You will always end up with a North Pole and a South Pole. You cannot have a North Pole and South Pole. Can I continue the process? Okay, if I can cut it into 1/8, as long as you have a magnet, you will always end up with a North Pole and a South Pole. At some point, if you continue cutting, you will end up with no magnet at all. The magnetic properties will be basically will disappear. So in that case, you lost both. So magnetic fields, and this is one of the items of the discussion today, magnets come in pairs, always, north, south. Okay. In other words, you cannot have a monopole, no monopoles. It's the same thing. You cannot have a monopole. It's the same point in here. So this is a critical piece of this is unlike charges for electricity. Electricity can have a positive charge by stripping electrons off of the molecule or an atom, for example, which is part of a molecule, which is part of a substance. Okay, if you strip the electrons off of it, what you end up with is a positive charge. Take that positive charge and to do whatever you want to do with it, so it's positively charged. Or you can dump excess electrons to the same material or different material and end up with a net negatively charged material. So in this case, you have a negative charge. So you can always carry it with you, do whatever experiments you want to do with it. So charges, like for example, in an electric discharge from the lightning, they can be isolated. So you can isolate a positive charge or you can isolate a negative charge very easily. Whereas for magnetic fields, you cannot isolate a pole by itself. You cannot have a North Pole by itself, and you cannot have a South Pole by itself. This is actually one of the ongoing topics of research in physics that people are working very hard to do it. And there is some quantum effects that apparently some people are working on where they could do that. And if it's possible to isolate an electron, albeit instantaneously where the other pole is far away, basically removed, at least a local isolation where you can do stuff with it, okay? You can do calculations, you can do all kinds of interesting phenomena with it, okay? So at this point, we don't know how to isolate poles. They always come in pairs. No matter what we do to them, they always are in pairs, okay? So that is one of the properties in here. Let me go back to sharing the screen. So this is item 1 of the discussion, no monopoles, okay? So as I said, they always come in pairs. So if I take 2 magnets, and I already have a bunch of magnets in here, okay? If I take 2 magnets, like this 2 magnets in here, and if I line them up the way that they are lined up right now, I have a north, I don't know which one is north. Actually, I'll have to have a needle in here to check. This one is a north, this one is a south. They attract one another, and you can clearly see that they are sticking to one another. From the bottom, it's the opposite. The south is attracting the north, and at the end, I have a magnet that are stuck to one another. If you take the polarity and reverse it, and try to do the same thing as before, no matter what I do, as a matter of fact, they're repelling from each other. If I force them still, I am working against the strength of the magnetic field. Okay, it's very hot. Okay, if I let go, it's gonna flip and then rearrange itself correctly. Okay, this is represented by the so-called magnetic field. If I take this magnet, the same magnet I had in my hand, and sprinkle on them iron filings, those are the drops that people, you know, if you go to a shop, mechanical shop, when they work with iron, there is all of those tiny pieces of iron that fall from here and there. Okay, I mean, they look like little pieces of hair scattered around. You gather those and they become what is known as iron filings. We use them in the lab. We have them extensively in the lab, where we sprinkle them on magnets, and you will see them sticking in the magnets. Usually we don't like to do that directly because of the fact that it's very hard to remove them from the magnet. So instead what we do, we have a surface separating them, and then we put the magnet underneath. Usually it's a clear surface so that we see the magnetic fields, field lines that is, and we sprinkle them. They line themselves according to the magnetic field lines, to the forces of the magnetic field, basically. Similar to a bunch of needles, many needles. Each and every one of them is acting like this tiny compass, okay? So that's basically how they are working. So in here, what I do is I have a north side of this magnet, and I have a south side of this magnet, and I have a north side of this magnet, and I have a south side of this magnet. If I only have one magnet by itself, the field lines would look like they are paired. They leave the North Pole and they end up in the South Pole in these curved lines. Of course, if I move far away, the curve is bigger. If I'm here, they curve and they go outside of the picture and came back on this line. If I leave from this side, they curve actually on a bigger curve and they go around the screen and come out from the other screen here, and so on and so forth, okay? Imagine if you can leave from this side, you're going to end up from this side of the screen, and you're going to leave that screen, go to the other side of town, and then probably to the other side of the United States, and maybe to the other side of the planet, and even maybe to the other side of the solar system, or potentially to the other side of the galaxy, or even the other side of the universe, to come back from the other side and come in here. So if you ever are interested in visitors to the edges of the universe, those are the field lines. The field lines for this magnet, they actually go through the entire universe and come back from the other side. Okay. Obviously, for a finite magnet, it's very hard to find that line. But there is one, theoretical one. Okay. Anywhere outside or in below is going to come back from the other side, from below or from the other side. But they always leave the North Pole and end up on the South Pole. Okay. The idea is I bring two magnets pointing in opposite directions. So this field lines in here, it's showing that the north is attracting the south is attracting the south, and the smaller lines in here are attracting one another, and the two magnets will actually attract one another. So opposite poles will always attract, whether north to south or south to north. They're always attracting one another, okay? Now, in a similar orientation, if I take the north-south and in the same side north-south, the field lines behave in slightly different fashion. From here to here, the north, they come back to the south, from north to south, there is no problem in here. Same thing in here, from north to south, there is no problem. But in here, here's the problem. It's trying to leave the north and it wants to end up somewhere, okay? And the curve is supposed to cut through the second magnet, but it cannot, because there is another field line that is also coming from the other side, and they meet and they collide. So the field lines in here, they repel each other, as you can clearly see. And there is a zone in here where the iron filings are missing, because there is too much interaction in there, and that is repelling all of the iron filings in that zone. And the same thing in here, and even to some extent anywhere in between. As a matter of fact, the two magnets are repelling one another everywhere. So if I force them closer, the emptiness starts to grow for more and more and more and more, until it's very hard for me to find any iron filing between them. If I let go of them, they're going to flip. Okay, they go through a spin to rearrange the orientation so that they attract. Okay, the magnetic force is an interesting force in there. The math for it is not easy. It's not straightforward, as a matter of fact, because it's really it requires a little bit, first of all, more work, but the understanding is similar. I mean, the idea is similar to charges. The opposite charges attract and the negative, the similar charges repel. This is in a sense the same way. Similar poles repel, and opposite poles attract. So that is basically the idea behind it. The force in terms of distance also seems to affect by the distance. The closer the distance, the stronger the force. Same thing in here. If I bring them closer, this file starts to get more and more, and you will have a lot of them in between them, basically facilitating the strength. in terms of strength for the magnetic field, the denser the magnetic field lines, the stronger the magnetic field. That's basically in a nutshell. Okay. So the strength in here, if I bring them closer, there will be a repulsion. The field line starts to leave from there. So that's basically, there is not enough field lines. As a matter of fact, they cannot penetrate each other at that point. Okay, and here they actually connect. They're like hands, and they will attract one another. So the distance seems to be a factor. The closer the objects to one another, the stronger the magnetic force interaction. But it's a little bit more complicated. If I take element by element, it's an inverse square law, similar to that of Coulomb force, similar to that of the force of gravity. So it's always true, even in this case. Now, trying to understand exactly what causes magnetism in a material. When I was young, actually I was in high school, they had a single magnet and I was playing with it, and it was a lot of fun. And I'm sure everybody had a magnet at some point or the other of their lives, and it's a lot of fun, okay? So what I did was, it was on a cold night, and we have the heater, the electrical heater at that time, basically a small unit, going on in that small room. So I put it on a spoon, and I brought it from there, close from the source of heat, until actually the spoon started to change color. And it cooled. After it cooled, I tried to put it in any material, any iron, and it did not attract. It lost its magnetism. I was devastated. I went to my middle school teacher, and I asked him, what happened? Why did? And he told me that something that at that time, I didn't know what it meant a lot, but I remember it now. And he said, you reached the Curie temperature for the magnet. What is the Curie temperature? Let me explain what that is. First of all, in any materials, it doesn't matter, magnetic or non-magnetic, it's divided into tiny regions. Basically, you have an atom. Let's take metals, for example, like, doesn't matter, any metal, iron, or even sodium, if you can have pure sodium, which is hard to do, okay? You have the atoms next to one another, and this atom has its outer shell for the electrons. Remember, metal has electrons that are available to roam and free and go everywhere. So, and those are the ones that are outside, the valence electrons, not the inner ones. The inner ones are tied to the atom and they cannot do anything. But the outer ones, let's say, for example, you have one electron, the case of sodium, for example. That electron is going in one direction or the other. It doesn't matter. It's going in one direction overall. It may be floating in different directions. The next door neighbor atom has also one electron. They're the same atom, basically. And also it's going in a motion of some sort. The next door neighbor also to it has also the same situation, and the one from the bottom, and the one from the bottom, and the one from the depth, and the one from the depth. Now, if I take a region overall, well, materials are characterized by, for a region, most of the electrons, not all of them, they're moving in one direction versus the other. So they have a net current in that direction. So I have a region called a domain, and in that domain, most of the electrons are moving in one direction, resulting in a magnetic field pointing in a specific orientation. Most materials, though, like this material in here, don't have, overall, their average motion is 0. Because one domain is pointing this way, another domain pointing in this way, another domain is pointing this way, another domain is pointing this way, another domain is pointing this way. On average, they cancel. And you don't have magnets. On other materials like iron, when it's magnetized, this region has this direction, the other one has this direction, more or less, or even that direction, or even parallel to it, or slightly off this way. But overall, they're moving in one direction. So most of the regions, they align themselves in one or the other direction until all of them are perfectly aligned. We reach the point of saturation at that point. So initially, at that point, they're fully magnetized. If I put them under heat, like I did, well, you randomize the motion overall, and the magnetic properties are lost. You need to magnetize the material again to retain its magnetism. Again, what you see in the picture in here are different regions of the material. They are well exaggerated. They are a lot less than this picture. But as you can see with the blue lines in here, these are what is the known as a magnetization or the direction of the magnetic field. Most of the time it's random. Most materials are random. Some materials though, like the ferromagnetic materials, they have a property, if they're aligned, they help one another to stay aligned. And they remain. After you remove what magnetizes them, they stay. I mean, this one is pointing up because its neighbor is pointing up. That's why it's pointing up. This one, though, is pointing up because its neighbor is pointing up. They lean on each other. You hold my back, I hold your back. That's basically what they do overall. And they stay magnetized. Some other materials, they don't do that. Some other materials, the minute you remove the magnetic field, they go back to their random motion. They basically orientations and they cancel each other, okay? So this is basically how the difference between a magnet and another. What causes, again, magnetism? I already mentioned the fact of the motion of the electrons. They're overall the ones that causes magnetic field. And it's true. If you have a current running through a wire and you bring a needle close from it, you will see that the needle will point to one direction or the other. If you increase the magnetic field, you're going to increase the current, you're going to see the needle will spin faster. That means the magnetic field is stronger. So the stronger the electric current, the stronger the magnetic field. No current, no magnetic field. You reverse the polarity of the current. Let's say the current was going up. Now you push it backward, magnetic field will also go in the opposite direction. So this is some of the properties of the magnetic field. So what creates a magnetic field, again, and this might be a question that somebody might ask you, you're walking in the street or you're going somewhere, you're going to the store, for example, and somebody might stop you, hey, what is the cause of magnetic field? So the answer to that is the current is the cause of magnetic field. So that's the second item of the discussion today already. So what causes magnetism are electric currents. Electric currents cause magnetism. You say, okay, wait a minute, hold on 1 second in here. What in the world is a current in a permanent magnet? I have a permanent magnet in here, and where is the current from? Where is the electricity coming from? Well, in this case, remember I described the way I described it is each atom has electrons moving in one direction, and the next door neighbor is one direction, and the next door neighbor one direction, resulting in an effect in a current. Let me draw the shape so that it's clear about that. So let me stop sharing the screen. Let me go back into my notes, and let me go back to physical science, and I had a page. And this page, I'm going to call it week 9. Okay. And I'm going to share now my note. Let me pick up a pen. Okay, let me explain this point because it's an important point that somebody might ask you a question about it, and I'm going to explain. Okay, we said currents create magnetic fields. That's the bottom line. So we want to understand what's going on with the permanent magnet. So I have an atom in here, and here it's an electron. It's moving in this direction, for example. The next door neighbor atom also has an electron that is moving in the same direction. The next door neighbor has an atom that is moving in the same direction. This one also moving in the same direction. This one also is moving in the same direction. And this atom also is moving in the same direction. I mean, I can probably draw another row of this in the same direction and the same direction. And in the same, all of the directions I chose are going against the clock. Usually the clock ticks this way. I chose this direction to be in the opposite direction, counterclockwise. So in this point between the two lines, you have one current that is going this way and the other current that is going this way. So they cancel each other actually. This point, this current is going down, the electron is going down, and the other electron is going up. So they cancel each other. this point in here, this current is coming down and this current is going up. Say they cancel each other. The same thing. This current is going to my right, and this current is going to my left. So they cancel each other. This current is going up and this current is coming down. So they cancel each other in here. Same thing in here. This current is coming down and this current is going up. They cancel each other. The same thing in here. This current is going left and this current is going right. This one and that one. So they're going, this one is going to my right and the other one is going to the left. So they cancel in there. Same thing in here. There is a cancellation. One coming down, the other one is going up. Same thing in here. This one is going to my left and the other one is going to my right. The same thing in here. This one is going down and this one is going up. And finally, this point and that point, this one is going to my left and this one is going to my right. They cancel everywhere. So inside that block, internally, where the charges are moving, they cancel. However, let me take another pen in here. Let's look at this current in here. So this is going up, and here it's going up, and here it's going up. Now it's going left. Now it's going left. It's going left. So it's going down now because following this electron, and this electron is going down, and this electron is going down for this one too. And now this one is going to my right, and this one is going to my right, and this one is going to my right, and it closes. So the entire current looks like it's going through a loop in here. It's not going anywhere because it's going on a big loop, but it has an effective current, as if I have a wire of a current going that way. So it's going to create a magnetic field that is going to come out of the screen. So it's going to create a magnetic field that is going to be coming out of the screen. Actually, this is the direction of the magnetic screen, the magnetic field. So it's coming out. This is like the arrow, for example. When you see an arrow, the pointy side of the arrow, it looks like this. Whereas when you see it from the back, it's going to be like this. Okay. So at this point, it's coming out of the screen. If I chose the clockwise direction instead of the counterclockwise direction, I would have found the magnetic field to be going into the screen. So this is the idea what's going on in a permanent magnet. So in a permanent magnet, the story is that each region, which is called the domain. So this becomes my domain. So this becomes a domain. And the domain in this situation looks like this, where the magnetic field is coming out. If I flip the domain, because the domain is actually a 3D object, it's not a 2D object. If I look at it from this side, for example, it looks like this, probably, and the magnetization is pointing that way. So I'm looking at it from here, not from the screen. I'm looking at it from the side because it's a 3D object. So that's the net of the magnetization of that material, of that region of the magnet. And this is true for the next door neighbor and the next door neighbor and the next door neighbor and so on and so forth. In a permanent magnet, they align more or less in the same direction. I think I spent enough time on this. Hopefully it's clear. So let me go back to the screen in here. So that's really the bottom line, is current causes magnetism. That is really in a nutshell. So if somebody asks you what's going on in a permanent magnet, well, in the case of permanent magnet, you have permanent currents that are due to the motion of the charges inside. Okay. If we get into a little bit more quantum mechanics stuff, the topic is a little bit more complicated because there are many contributions to the current. But at this point, this is good enough for the topic. Okay. The direction of the magnetic field, which is a very, very important topic too, is given by the so-called right-hand rule. Let me explain the right-hand rule. Okay. The current is moving in this direction, for example. So this is the current I. The magnet in this case, from the top, the magnetic field from the top is coming from the screen and is going around. When I get into this point, it's going into the screen, and then it comes from the other side. If I take my right hand and the thumb pointed, it has to be the right hand. If you're left-handed, you're out of luck. You still have to use your right hand. So if this is where the current is, this is how the magnetic field curls around the current. So if this is the current, this is how the magnetic field curves around the current. You cannot use your left hand. If this is the current, you tell me, oh, how's that? No, it's not going to work. It has to be your right hand. So this is one version of the right hand rule. There are at least another version of the right hand rule. And I'm going to mention it here since we need it too. Okay. When you have a charge, this is a charge, Q. Let's take it positive, okay? Because the charge matters, the sign for it matters. And it's moving in this direction, so this is the velocity. So think of it as a positive charge in motion, bang, going around, okay? And let's say, for example, it's inside a magnetic field that is pointing that way. This is the symbol for the magnetic field, by the way. So if you see the letter B, most of the time, this is the magnetic field. Sometimes they use a different symbol for the magnetic field, the letter H, but then there is a little bit of subtlety between H and B. One of them is actually has a constant multiplying one another, that's all. But if you see the B, that's most of the time, 90% of the times, people use the letter B, okay? Sometimes, and the upper division classes, they use different one, they use the H. But by then, you know exactly what the H stands for. There's a slight difference between them, okay? So forget about the H, let's use B, because that's what most of the time the books, at least at this point, they use, okay? So that's the magnetic field. So think of, this is the direction of where the electron is, and this is the direction of the magnetic field, okay? So if that's the case, then where is the force? This electron will move now, will be affected by this magnetic field, and it's going to bend in this direction. This charge is going to bend in this direction by this force. So this is the force that is due to a charge inside a magnetic field. And in this case, the rule is using still the right hand, but a different right hand. Not the curling I described before, but this is where the charge is moving. It's a positive charge, though. This is where the magnetic field is, where in this case, this is where the force is pointing, okay? So if you ever saw musicians using their hand and holding it that way, that's what they're doing, actually. They're using the right hand rule, okay? This is the direction of the velocity for a positive charge, okay? This is the field, magnetic field, and this is the force where they're pointing. You say, okay, what happened if the charge is not positive but rather negative? Then in this case, the only thing that's going to be done is reverse this force. So always use a right hand rule as if you have a positive charge. And if somebody tells you, hey, the charge is actually not positive but negative, then in this case is going to point in the opposite direction, because the force actually is proportional also to the charge. So if the charge is negative, then that negative sign will flip the direction of the force, that's all, okay? Other than that, that's how the rule is. The right hand rule is a very, very important rule, okay? RHR, right hand rule. Okay, for the current, it's easy enough. You have the current moving this way, and then you have the magnetic field created by that current pointing in the same direction. Now, if we follow the same rationale, actually, we can find the effects of a magnetic field on a current carrying wire. So imagine with me that you have a magnetic field pointing in this direction. This is B. And you have a wire now that has a current running through this way, I. Well, it's easy enough now. I is a charge is moving one direction, and the magnetic field is pointing upward, so the wire will bend in here to the due to the force. So it's going to come out of the screen. So it's going to come out. It's going to bend this way, okay? So that's easy enough for us to understand. So this wire will bend in this way. Now, if the current is moving in the opposite direction, this way, and the magnetic field is still pointing this way, so this is B, and this is where the current is, then it's going to bend into the screen because the positive charge, because of the again, the argument I was making about the sign earlier matters, okay? Furthermore, if you take two wires that have currents moving in the opposite directions to one another, let's see what's going to happen in here. This wire, so there is a current in here, and then there is another current which may or may not be the same. So, okay, I'm going to call it I prime just to make a point in here. So there is a current, there is a magnetic field that is going to circulate because of the right-hand rule. Okay, so at this point, the magnetic field created by the first one will go into the screen. And here is going to be out of the screen, but who cares about that? That's not important because, again, we are not talking about that one. So in this case, it's going to bend into the screen. So again, the magnetic field is going this way. So if I use my right-hand rule now, I have the charges this way and the magnetic field into the screen. So this wire will move away. Sorry, did I say move away? Wait a minute, wait a minute. I'm sorry, I got it backward. I got it backward. So the current is going this way. The magnetic field is into the screen. Yes, it's going to move away. That's correct. So the representation is correct. Okay. Let's see what happened to the other one. To the other wire. So again, I have a current this way. Now it's actually this region of space, and it's this region of space. Again, the right-hand rule is going to go into the screen in here. And then here it's going to come out of the screen because I just flipped the current for I prime. So the magnetic field created by the second wire into where the first wire is going to go also into the screen. So let's see what's happening here. So I have the current this way and the magnetic field into the screen. So it's going to be bent upward. Two current carrying wires in opposite directions repel each other. This is strange. Usually things of the same direction repel, like charges, like poles. But when it comes to current carrying wires, actually the opposite will repel. How about the same direction? Let's see what's going to happen to the same direction. Imagine with me that I have a wire that has a current going this way and another wire that has a current going in the same direction. This wire will create a magnetic field that is coming out of the screen in here and it's going into the screen in here. So the magnetic field is still going into the screen at this point where the other wire is located. For the other wire, the current is going this way, the magnetic field is going into the screen, and the force must be then pulling it upward. So it's going to be attracted upward to where the other wire is. Now for this wire, it's going to create its own magnetic field given by the right-hand rule again, where it's coming out of the screen in here where the other wire is, but it's going into the screen somewhere in here. Who cares about that for right now? So it's coming out of the screen. For this wire, it has a current coming this way, and the magnetic field is coming to me. So the force is coming down in here toward the other wire. They're attracting one another. Two current carrying wires in the same direction attract each other. That's what I'm saying here. So there is a force of attraction. This is unlike anything we have seen so far. We have learned that positive charges and positive charges repel, negative charges and negative charges repel, similar charges repel, period. We've learned also that opposite charges attract, positive attracts negative, and negative attracts positive. That is done deal. We also learned that north repels north and south repels south. Similar poles always repel. We learned also that opposite poles, north attracts south and south attracts north. Opposite poles always attract. Now, when it comes to current carrying wires, it's the opposite. In the same direction, they attract. In the opposite direction, they repel. So that is an exception to what we have seen. And that is an interesting phenomenon in here. So let me stop sharing the screen and go back and share. Why is this thing keeps on popping up? I don't want to do this. Dismissal, reminding you of an event which I'm not attending. Okay, so let me share the screen again. Let me go back and to make sure that it's still we're on the same page. Share. Again, I mentioned the right-hand rule and how the current is. So you can do it this way too. This is where the force is, okay? You can also use it this way, okay? So you have a current, you have a magnetic field that is curling in that direction coming out. So the force is going to be this way, okay? So it's the same thing, always the right-hand rule that comes into play. Which brings me to another interesting point, which is either the power generation or the motors. So let me stop sharing the screen and let me share my notes again. Let me describe the generator of electricity first, okay? So think with it this way for me. We have a permanent magnet, for example, where the north is and the south is, and we know the field lines are pointing in this direction. So these are the magnetic field lines. And let me change color in here. Let me make it red. Let's see, we have a wire inside in here that looks like a loop. And this points in here, they're extended, okay? So at this point, let's say, for example, this is spinning. For some reason, let's say, for example, we have a waterfall, and that waterfall is driving a turbine, and that turbine is causing this wire to turn. So the water is basically continuously pushing the end so that it's always turning, okay, one way or the other. So in this case, of course, it should not touch this because water is a conductor because of the salts in it. There is always an insulation in here, but because this is spinning now, because of external fashion, then in this case, I have a magnetic field that is changing in the region. The magnetic field is not changing. It's the area where the magnetic field is changing. In other words, the field lines are changing. And the law that is described in here, an electromotive force, in other words, a current, if you connect these two ends to a resistor, for example, or light bulb, for example, okay, obviously, because of this motion, you really have to be careful. You have to design a way so that it touches the light bulb, but then it doesn't drag it with it, okay? Because if it drags it with it, or if it drags it with it, so what, okay? They're going to have, in this case, if it is spinning in this direction, you have the field lines that are changing inside that area, inside the surface. Sometimes you have more of them when they are perfectly parallel, and then it's going to shrink until they are anti-parallel, and then it's going to grow. And the law that is described in there, which is due to Mr. Faraday, says that the rate at which the field lines, which is in this case the product of the magnetic field times this area is changing with time, is going to be the rate at which that is changing is going to be a voltage difference in here, and a current will be established. So that's how power is generated. The opposite of a generator, so this is a generator. The opposite of a generator is a motor. So motors, they are in a sense similar. Here is a motor. Similar, you have in here two magnets, okay? And actually this one could work as an EMF. This is actually a generator if I move it this way, okay? Because in here I have a bunch of loops and I have a magnetic field that is penetrating from one end and trying to go to the other end. Let me stop sharing the screen to explain how this picture works. And I may even have to probably, yeah, that's fine, okay? So think of this loop in here, okay? First of all, it's not one, it's many, many turns, okay? And there is a magnetic field line that is going from one end to the other. As this one is spun, let me spin it from this side. as this one is spun, the field lines change in one side or the other, okay? And then electricity will be drawn from these two ends. That's one way. If I do it the opposite, if I connect this to a battery here and there to the battery, okay? And turn on electricity, what happened in this case, this starts to spin on its own. So a generator and a motor are opposite to one another. So this could act as both. If I spin this one externally, fast enough, it has to be super fast, and I put it in front of a voltmeter in here, an ammeter in here, I will see a current flowing through this one or even a voltage generated. If I do the opposite, if I bring a voltage, a battery in here and connect it, this starts to spin on its own. So this will act as a motor. So a motor and a generator are opposite to one another, but they always require something key in this whole process, okay? A varying magnetic field flux. What the flux is, the flow of the field lines, okay? It's a fancy way of saying how many field lines are going through an area, that's all, okay? It's like the flow of water over a cross-section of the river. If there is too much flux, that means there's rushing water coming through, gushing through this whole thing, or you have a big area, okay? There is still a lot of water. So if you take, for example, a stream of water versus a big river, of course, a big river have more flux of fluid than a small, basically, side. So that's really what that word is. In other words, how much fields are going per unit area. So that's really what the flux is. So if that changes, so in either case, you have to change this. Then in this case, it introduces an electromotive force or battery, basically. That's what the electromotive force is. Electromotive force is the force that moves an electron or charge, okay? So that is basically in a nutshell what that is. Which brings us to another concept, which is the concept of transformers. You can clearly see this one is from a high voltage line, bringing down the current down to your house to bring it down to a manageable number, okay? So this is usually in the neighborhoods, you'll see this ones. But what a transformer is basically one side to it, it's called the primary, and the second side in here, it's called the secondary. So what's going on in the primary, you have a current running through it. And that current, as I was explaining, creates a magnetic field. That magnetic field is running through this whole material in here, okay? Now, if this current changes with time, the magnetic field that is produced will change with time, which means in here, you will have a time varying magnetic flux. There is no current initially in here. So the current flux in here, the flow of the magnetic field will change in here because this one changes with time. So this one also will change. The flux of how many field lines go up and down will change. That will induce then an electromotive force. If you connect these two ends to a light bulb, you will see light on this side, on the secondary. So this is a transformer, a typical transformer. It's the same thing in here, in all of this different formats in here. What distinguishes a transformer from another transformer is the ratio of the turns in the primary to the secondary. Okay. Let's say, for example, you have 100 turns in here and you have 50 turns in here. Okay. Well, in this case, it's a step down transformer. If you reverse the process, in other words, your phone, you want to charge it. You want to charge your phone. Okay. And the phone on the power, it says 5 volts. That's all it needs. Your house drains 120 volts of an AC current first, which is a problem. Okay. It drains 120 volts. So you need to bring that 120 down to 5 volts. So you need a transformer. So your charger for the phone, whether the USB type, it doesn't matter what type you have, has a transformer inside. Okay. And transformer in practice looks like this. At least in electronics, it looks like this. In big industry, it looks like this, or it can even be bigger, much bigger than this one for extreme high voltage lines. Okay, So this is a low voltage device, so it doesn't require a big transformer. For your phone, it's even smaller, but it brings that 120 down to 5 volt. So this is a step down transformer. Most of the transformers out there are step down transformers. Okay, even this one, the one the power company delivers to your power, is a step down transformer, because in the power lines they have extreme high voltage and they bring down your voltage down to this one. It's all because of magnetic field, because without it you cannot, you have to have a magnetic field produced by the primary and that magnetic field need to change with time, which makes a very good point in here that transformers do not work with the direct current, work only with the alternating current. Because if there is a current in here and it's not changing with time, the flux in here will not change with time. And if there is no flux changing with time, there is no electromotive force. So this is a varying magnetic flux. It has to change. If it's not changing, then in this case, forget it. So the transformers only work with alternating currents. They do not work with the direct currents. And that is the idea behind transformers. Again, you could have extremely high transformers, and usually step-up transformers, they're used by the power company to take the voltage from the dam, for example, increase the value, send it through the power lines. Then when it's in the town, they bring it down and down until it comes to the consumer at 120 volts. And even then, you're not going to use 120 volts. Your computer, I mean, your laptop probably is using 18 volts, 20 volts. So it's going to bring it down from 120 down to what it needs it to. So depending on the electronics, it's not going to use all of the 120. Okay. Some devices at home, they use actually different voltage, 240 volts, and those devices require actually different kind of wiring, because it's still using 120 volts, but it wires it so that one of them negative 120 and the other one is positive 120, resulting in a net difference of 240 volts. What you need for your washer and dryer and all of this big electronics. Sometimes even refrigerator units, they require some different voltage requirements. Anyway, this is basically the unit. The Earth is a big magnet, and it's actually a very useful magnet because of the fact that without it, the fast-moving charged particles that are delivered from the sun and probably from the cosmic radiation will come straight to us and hit us, and basically they have extreme high energy and they can cause far more damage, and life would not exist without this protection. So the magnetic field of the Earth is actually is useful, and the entire Earth is a big magnet, that's all, okay? And so the charges actually are deflected either away or towards the North Pole or the South Pole. And they produce those aurora borealis or aurora australis, or those basically northern lights and southern lights and all of these things. So this is the unit in a nutshell. Let me see how much time we have left. Oh man, we don't have a lot of time, but we should be able to probably cover some stuff from the homework. So again, the live discussion is going to go here. The previous week notes from here. This is this week's notes. So let me pull the homework and start working on it. So problems are from pages 215 and 216, and you have 45, 46, 47, 55, and 57. Okay. I hope that you guys have the book with you guys. And I don't have the book with me in here. So let me put my notes. Let me put this on one side. Let me stop sharing the screen. Put it on this side. And let me share my notes again. And hopefully you guys have the problems ready while you're doing this. Again, the homework is due October 22nd. Okay. So in about 2 weeks, or less than 2 weeks, actually. Okay. So problem 45, it says you have a 12-volt battery. So this is problem 45. Let me change the color again. So you have a 12-volt battery and moves 4 coulomb of charge from one terminal to the other. Show that the battery does this much work. Again, we talked in the lecture that the work, or the energy in this case required to move 4 coulomb sitting between 12 volts is basically Q times V. So 4 coulomb times 12 volts is 48 joules. So it's easy, straightforward, okay? But you have to remember this one in here. So 46. It says, suppose you could, this is from the previous chapter, by the way, all the problems are from the previous chapter, not from this chapter. Suppose you could expend 10 joules of work to push 1 coulomb charge particle against the electric field. What would be its charge of voltage? If the particle is released, what will be its kinetic energy as it flies past its starting point? Okay, here is the point. So we need to spend 10 joules of energy to move a charge of 1 coulomb, okay? So how much voltage is needed? If we go back into the same expression, QV, the voltage is going to be U over Q. Remember, I have 10 joules of energy divided by 1 coulomb. That is actually 10 volts, okay? So 10 volts is required in here. If the particle is released, what will be its kinetic energy as it flies? Okay, if it's released, remember the energy, U, which is 10 joules, must all of it be converted to kinetic energy. So this is the kinetic energy because of the conservation of charge, conservation of energy. So the energy, initially, it has no kinetic energy. At the end, it will have no kinetic energy, but just no potential energy, but just kinetic energy. So in this case, it's going to be just 10 joules, basically. So if you start with 10 joules of electrical potential energy and you let it go, and then how much energy you're going to end up with in terms of kinetic energy, you're going to end up with 10 joules. Start with 10 joules in one form, which is potential. It is going to be converted into kinetic at the end of the day. So that's easy, okay? So at the end of the day, you have 10 joules, okay? They didn't ask us how fast it was going to be moving because they didn't give us a mass. If they give us a mass, then we can tell how fast it's going to move. Remember, the kinetic energy in 1/2 times the mass times velocity squared. So if I know the mass, I can multiply 2 by 10, this 10 joules, and divide it by the mass, and then I have how fast the velocity is moving. I have to square root it, though, to find what the velocity is. So that's not asked, so forget about it, okay? We don't have to waste time on that question since it was not asked. Then 47, it says, the potential difference between a storm cloud and the ground is 100 million volts. So V is 100 million volts, or 10 to the power 8 volts. That's what the potential is. If a charge is 2 coulomb, flashes in a bolt of light from a cloud. So we have 2 coulomb that flashes. By the way, 1 coulomb is a big number, so 2 coulomb is still a big charge from lightning. Show that the potential energy is this much. Again, we're going to do the same thing. U is equal to QV, and Q is 2 coulomb times 10 to the power 8 volts. So it's going to be 2 times 10 to the power 8 joules, or 200 million joules. Man, it's a lot of energy. That's why lightning is dangerous, because of the energy. 55. It says a dehumidifier with the resistance R. So the resistance, as you're reading these problems, it's a good idea to take notes, okay? Please be more verbose in your answers, okay? Do not, I'm talking while I'm writing, so you guys need to write because you're not talking, explaining your process, your thought process about these things, okay? A lot of these problems are easy and straightforward, but you have to understand them first, okay? So the resistance is 20 ohms, okay? And the current is 6 ampere. When connected to an electrode, show that the power consumed by this iron is 720 watts. Again, the power is actually R times I squared. This is part of the notes from the lecture. Okay. The resistance is 20 ohms. And the current is 6. But don't forget, you're going to square this number. So 6 times 6 is 36, times 20 is going to be 360 times 2, which is 700. And 36 times 20 is 72 times 10, that's 720 watts. That's the power. So this is the power. Okay. And this is the ohmic heating. And that's what heating. And that's what the dehumidifier uses. It basically has a resistor in there, and it throws the air through it, it warms up, and basically gets rid of the humidity. Okay. Number 57. What are we doing on time? Still have a few minutes. Good. 57. The total charge that an automobile battery can supply without being recharged is given in terms of an ampere hours. A typical 12-volt battery, so remember, the battery has a 12 volt. So this is the battery. We call it electromotive force. Electromotive force. Basically, like this battery in here has an electromotive force of 1.5 volts. Okay. The battery of the car has 12 volts. Has a rating of 60 ampere hours. 60. So this battery has a 60 ampere hours. Okay. This is how much energy is going to give you. 60 amperes for 1 hour, 30 amperes for 2 hours, and so on and so forth. Okay, that's what that is. For 4 hours, it's going to give you 15 amperes each time. Okay. Suppose you forget to turn off the lights in your back parked automobile. If each of the headlights draws 3 amps, so you have 2 headlights, and each one of them draws 3 amps. So we have 6 amps that is drawn. Show that your battery will go dead in about 10 hours. Okay. So in this case, the current I is 2 times 3 amps, which is 6 amps. Okay. Since this battery has a 60 ampere hours, the battery will run out of that much juice basically in about how much? 60 ampere hours. Okay. And it's using 6 amps at a given amount of time, because it needs time to drain this much. Obviously, 60 divided by 6 is going to be 10 hours. 60 ampere hours over 6 amps is going to be 10 hours. So in about 10 hours, the battery will go dead. Okay. Obviously, if you have turned on the lights, that's not the only thing that is draining power also. So you don't have those big lights only, you have small lights, and you have other lights, and you have all the electrical circuits that also have resistors in them, so they drain more. So probably it's going to run out of battery out of juice in about 10 hours, less than 10 hours, probably 8 hours, 7 hours, depending on the electrical wiring of your car. Okay. 58. Okay, show that it costs 7 cents to operate a 25 out. So we have a light in here that is a light bulb that is 25 watts. It's not a super bright light, by the way. 25 watts is a dim, especially if it's an older one, the tungsten one. Okay. Light for 24 hours, if the electrical cost is, so it costs 12 cents for each kilowatt hour. Okay, every time you consume 1 kilowatt hour, this power company charges you 12 cents. Okay, so that's how much the rate they charge you at. and you have a light bulb that is 25 watts, and you left it for 24 hours. So how much that will cost you? Well, we need to find the power, how many kilowatt hours we consumed first. So the battery is 24 watts, and it's been running for 24 hours. So this is how much energy in this case is consumed. This is the power consumed. I mean, the energy consumed. So the power is the rate at which energy is drained. That's what the power is. It's work over a time. And this is the time. So this is going to give me an energy, which is 24 times 48. Let me get the calculator quickly in here. Where is 24 times 25? I'm sorry. I don't know where I got 24 from. It's 600. 24, it's not 24 watts, it's 25 watts. Okay, times 24, that is 600 watts per hour. Watts hour. That's how much energy you consume. But you don't want it in hours, you want it in kilowatts. You don't want it in watts. So you have to divide by 1,000, and you have to divide by 1,000 to find 0.6. That's when you divide by 1,000. Instead of watts, you want it in kilowatt hour. That's what you want, kilowatt hour. So that's why you divide by 1,000 in order to convert watts into kilowatts, because a kilo has 1,000 in it. So 0.6 basically kilowatts. It's not much energy, but it's there. The company charges you 12 cents though for 1 kilowatt. You didn't consume 1 kilowatt. You consumed just 0.6. So the cost is the rate, which is 12 cents per kilowatt hour, times the actual usage, which is 0.6 kilowatt hours. Obviously, the kilowatt hour cancels the kilowatt hour. 0.6 times 12, which is 7.2 cents. Doesn't make sense to say 7.2 cents, but that's what it is. Because it's a cents, the company will charge you 7 cents. Okay. I mean, what is 0.2 cents? Are you going to take a penny and get it and give it to them? That's not how it works. Okay, so they're going to charge you 7 cents. They rounded down in this case. Okay, so it's a good example of rounding down. Okay, I went through the entire homework set. Okay, so hopefully you guys are following. So we had 2 discussion items. The first one, no monopoles. And the second one is that electrical currents cause magnetism. So those are the 2 topics. And I'll see you guys next time. And if you guys have any questions, please let me know. So I'm going to stop the recording.